This also gives us opportunity to have international guests without having the troubles of long-term traveling. So we welcome today Angelos Vourlidas. He will give us a talk and an update on a wide field imager WISPR science results from Parker-Solar probe. So just for those of you who don't know Angelos, I will give you a short introduction. So Angelos received his PhD in 1996 on ground-based radio observations of the solar corona, and had a postdoc stay at Caltech. Then he moved to NRL, to the Naval Research Laboratory, and is since 2014 the solar section supervisor at the Johns Hopkins University Applied Physics Lab, where he focuses on the physics of solar corona and solar eruptions, and especially on coronal mass ejections and influence on the geospace environment. Angelos, as he gives us a talk today about Parker-Solar probe, is also very heavily involved in space missions. STEREO, I guess everybody who worked with STEREO image data, SECCHI knows Angelos' papers, and also in other missions. So yeah, today he will give us an update on Parker-Solar probe, on WISPR. And with that, I would like to ask Angelos to start with his talk.
Yes, thank you, Manuela. I'm very happy to be here, and good afternoon to everyone. I guess it's the new mode of doing business, to do it on Zoom. It's not bad actually, because then we can actually see each other, even though most of us are still on lockdown. So I'm very happy to see familiar faces and to meet new people. And so Manuel asked me to give you some update on the recent mission on the Parker-Solar probe. So I try to focus on our telescope, the WISPR telescope, on which I'm the project scientist, and so give you a rather quick overview of the science results. I mean, it's a little bit too early to get into too many results, but at least I want you to familiarize yourself with what WISPR is doing, and a bit on how we actually do the observations. This is a very different type of mission than what we are all used before with STEREO and SOHO and the other Hinode and IRIS that are from Earth. And would like to then leave some time to discuss also at the end, some of these issues and unusual, I would say, approach to science analysis. So I'll start with, first of all, for an overview for those of you that maybe not be familiar with the mission overall, because I'd like to put a context. Now, the mission, of course, goes after some long-standing solar physics problems, like most missions they do, and it really touches on three key questions that have been sort of bothering us for a while, even before I started in this business. So, of course, one is the all familiar coronal heating problem. Why the corona is so much hotter than the surface, which actually feeds into the next question of how does the solar wind originate, which originally was thought that it was just the thermal expansion of that plasma, but now we know that the question is a bit more complicated than that, and it's fundamentally, the solar wind fundamentally is our connection to the sun, and why it has such a societal relevance to all of us. And as part of the solar wind, of course, is what most of us are really keen on, are the coronal mass ejections and energetic particles they accelerate, which has been quite a bothersome issue. Where those particles come from, whether they come really from the flare or as the cartoon shows here, whether they come from the coronal mass ejection. That question has a more increased, quite an increased relevance lately, at least in the US, because of the return to the moon directive that NASA has to fulfill, and therefore, and of course, eventually, as the picture shows here, to have habitats on Mars down the line. So once basically you have astronauts out of the protective magnetosphere, you have to deal with energetic particles. So Probe, of course, is not a space weather mission. It's supposed to study fundamental physics. And the way we do that is by going very close to the sun. This is an animation of the Parker Solar Probe orbits, which uses Venus for gravity assist to come in closer, ever closer to the sun. And then, as you see here in the like right here in the movie, that every so often we come close to Venus, we can use the assist to drive the orbit a little bit closer. Then we stay for a few orbits until the next opportunity, and eventually we get to this quite impressive distance from the sun of less than 4 million miles, which is quite close in astronomical terms. Now, the one thing you should notice in this movie is, of course, that a lot of things are moving around, including the Earth and the probe and planets and solar orbiter since February. So that means that the way we approach the science, how we approach the science and maximize the science return from the mission requires us to consider all of those assets during any given time of the mission. You know, we have a more complex sort of ballet of players around that we need to organize to maximize when we're taking the observations and what type of observations we're taking. And I'll go into this more, and we can discuss in the end. But this is sort of what I would like you to remember from this display. Now, before going to the details of the orbit, here's a typical, presentation of what probe carries. Because it goes so close to the sun, we have, of course, we require a thermal shield up front, which has a very high-tech technology, which we can talk about later. And because, of course, we're going close to the sun, we need a lot of delta V, and we have to expend a lot of energy to drop so close to the sun. That really puts a constraint on the size of the spacecraft. So the spacecraft is quite small. It's basically 3 meters tall, 4 meters tall, sorry, and about 1 meter in diameter. And that restricts the amount of instruments you can have on. And now on the left side, you see sort of the apart from some instruments, we have the boom for in-situ instrumentation. This is the Fields instrument that has 4 antennas that actually face in the solar wind and the solar heat straight on. And then there are some magnetometers on the boom to measure both radio and magnetic field. And then we have sweep, which does the solar wind measurements, superthermals, protons, electrons, and potentially helium and oxygen, maybe. And the energetic particle instrumentation called ISIS, with both high and low energies, and of course the imager, which I'm more familiar with, which is located on the RAM side and is providing the context, the imaging context, large-scale context into which we can sort of interpret the in-situ measurements. Now, on the left-hand side, there are some unusual things for a spacecraft. We have here the solar array cooling system. Basically, we get so close to the sun that even though we only allow a very small part of the arrays to be illuminated, this is the whole array that is illuminated when we're out in Venus, but then it folds in and allows only, if I don't remember, I think 10% of this area to be illuminated. Still gets so hot that you need to carry water coolers, which is quite heavy and really restricts the amount of payload you can have on. And then we have the heat shield, like I said, that it can face up to about 1400 degrees Celsius of heat in the front, but then in the back there's only room temperature, 20 degrees C. So it's capable of basically dispersing 3 million watts of heat or energy in this width of only about, I think, 10 centimeters or so. So it's quite a technology right there that enabled this mission It's been on the books, I guess, since the beginning of NASA. Now, where we stand now, this is an orbit profile showing the different perihelia. So we started in August 2018. We had 3 perihelia at the same distance from the sun, 0.16 or about 35 solar radii. And then you see here the gravity assists from Venus that allow us to step in slowly. And we're doing this because, of course, we don't know really anything about the environment so close to the sun. So it's more of a risk reduction approach rather than say a scientific approach. We want to go slow in and avoid damaging the spacecraft if we can help it. So far we have done 5 perihelia. We just finished the last one on June 11. The perihelia basically are we use numbers to refer to them. It's a good nice shorthand to know what you're talking about, because really the science is not a continuous stream of data like it is, say, from SOHO, but it is sort of focused in this perihelia. And so like I said before, depending on the particular relative orientation of Earth and probe or other assets, there will be different science targets for each perihelion. So it is good to familiarize yourselves with the numbers and to keep this in mind when you're looking for data, for probe data. Now, the perihelia really defined, as you can see here, from between the aphelia, basically as we call it, the encounter 5, E5, starts when we just leave our aphelion coming into the sun and ends when we reach the next aphelion. So this is the period that you actually might see in papers or when people give talks. They might refer to encounter 5 talk. That includes all that period. On paper, the nominal science operations or observations start within a quarter of an AU. That was the original plan, and that's what's marked here with a light gray. But since, of course, the first 2 perihelia, the engineers, got more comfortable with running the spacecraft, so they have released some margin, and now we have extended. We have doubled the period of science observations from plus or minus half an AU. Now that's not always going. That it's not going to always be true that we can take continuous observations during that period. Depends a lot on how far probe is and what the downlink profile gets into details. But the in-situ instruments for sure will be operating on plus or minus half an AU, and with WISPR, we really trying to spread out our telemetry so that there will be at least some sort of synoptic coverage throughout the orbit. And of course, we focus our high cadence observations or during the perihelia, but that's not always true. And we can talk about it a little bit later. You'll see as I go through the results that the science operations are a bit involved. Now we are on the way to Venus orbit. Now, we are on our way to a Venus flyby, which is July 11. That will drive us closer to the sun. Now, in the next perihelion, which is in September, we're going to be at 20 solar radii, and that's quite an important milestone, because 20 solar radii for many people is considered the Alphen radius, where the wind becomes super critical. So we'll see, right? This what's happening in 20R. So there will be 2 perihelia 20R. Then we're going to have another flyby in April, I guess, and then P8 will be slightly closer. Is it 15? No, I think it's about 18 solar radii or so. And after that, there is a period of quite a lot of several 1, 2, 3, 6, 7 or so orbits that were at the same distance. I think 15 solar radii. Then that's next year. and the year after that. So as you can see, this sort of different profile for every orbit kind of dictates a lot of how we think about the science for the future planning. Now to start on with our sort of overview of WISPR results, here is an image from our Nature paper. There was a special issue with 4 papers one from each instrument that came out early in the year from Nature, and so is the combined field of view WISPR. And we have a very slick movie that Johns Hopkins put together to describe the instrument. But as you can see here, the instrument is on the RAM side. It's outside facing basically the oncoming wind, and it has 2 telescopes. One is the inner telescope that looks closer to the sun, and the outer telescope that looks farther out. And for you that are familiar from SECCHI, this is similar to what we have on SECCHI with high 1 and high 2. Only we're looking much closer now. And that's it. We're just taking images. We don't have shutters. We don't have any polarization. We can take subfields and maybe in high cadence, but we mostly operate this quite similar to how we operate the highs, basically summing individual images to create enough CN to noise ratio to actually see something. That's because, of course, this is a very small instrument. It's at least half of the lateral size of highs, more like a shoebox. So that's the size. So small telescopes. There are other reasons for this apart from science. So this is a simulation that I have shown in the past of what we were expecting to see, and also that sort of captures the challenges here. You know that this is, of course, the simulation where will be the nearest approach to the sun, and as you can see, the frame rate is 2.5 days per second. And this is just to emphasize that during a perihelion, pretty much everything changes. Our background changes, the stellar background changes, the spatial resolution changes. So it is nothing at all like what we've done. We're accustomed to from STEREO and LASCO. And this is what we got. This is the first light images. So some of you may have seen this early on in November 2018. This is a very zoomed out picture where we have used some background techniques to remove the F corona. And it is a few days in duration. I think it is right through perihelion, so about three days, where you can see a CME with a very clear flux rope structure, at least flux rope the way we understand it, the observers, maybe not the modelers, followed by a few smaller flux ropes in the distance. And of course, this is superimposed on the background of streamers. You can see some potentially outflowing material. And what you see here as some sort of blob or moving is a planet. It's a planet, I think, is Jupiter, but it has been, because of the treatment, it ends up looking like that. Now, so this is how the treated images look like, and in the end, I can describe more of the data products, but if there's interest on that. Now, I'll go to different subjects on this, starting from the CMEs that I know better. There have been a few papers that came out on a special UpJ issue in 2020. Most of them basically dealing with the events, not most of them, all of them dealing with I think with events from the first perihelion in November 18. The last paper by Nieves Chinchilla is more in situ paper. The other 3 deal with WISPR observations. And so here is shows different events before I get into the details of CMEs. Now, starting here on the left, what I have is a projection of the 2 fields of view onto the plane of the orbit. And this is something that we don't do before. We haven't done before. And the issue, the reason for that is, of course, that the orbit is a bit inclined at 3 degrees from, it has the same as the orbit of Venus, 3 degrees from the ecliptic. And so and because we are so close, it does matter. If I don't project this, you might think, for example, that this CME that goes right through the ecliptic was actually at the North Pole or something like that. It's very, we call it confusing sometimes if you look at the straight data and try to compare it with other observations. Now this, of course, we can project it in different planes, like the the ecliptic plane, of course. But also this allows us to compare directly with in situ instruments, because since this is now the orbital plane, that means that whatever hits the spacecraft will be here at 9 degrees. I think this is 9 degrees. This one here at this point. Whatever passes this point will eventually be encountered by the in situ instruments, and that's what makes this sort of a useful representation. Here is another CME from the second orbit, April 2019. Of a few more CMEs. Again, you see that what you see here in the background are planets, and then this fuzzy feature is the galaxy, or the remnant of the galaxy after processing. Now, this is one of the problems we have, is that because of the orbital configuration and the date we launch, the galaxy is always in our field of view in every perihelion, right at the perihelion. So this is going to be an issue, getting clean images. The other thing you might notice here is a lot of streaks. And a lot of those streaks are not cosmic rays, but actually byproducts of dust hitting those cooling arrays that I showed earlier and creating secondary spallation products. Basically, they get those poor arrays, because they have a lot of surface area, they get bombarded by the interplanetary dust and create all this, I think they're like micron or even less, smaller particles that then get illuminated by the sun, and we see them as streaks in our images, and there are a lot of them. That's another issue. So, and this is from orbit 3. As you can see here, there's a very nice CME, that is preceded by flows, and you see in the aftermath of the CME, you see a broad arc, which looks a lot like the streamer. You see in the streamer expanding along your line of sight. What else do I want to say? And then as you notice here, you see these spikes that come and go. This is basically the stellar stray light from stars that as they approach the end of the edge of our field of view, there is a reflection in the detector. They're reflected through the system in the detector and appear as elongated features. Those are stars, and you will notice them quite often at the borders of the images. So, but basically what you see here is that the CMEs, they all look the same, which is what I've been saying all along, and a lot of us have been saying all along. They all look like flux robes, and that's what it is. But that's not great news. I mean, it's not surprising, at least to me. But the surprising, or maybe more surprising thing, is that we see a lot of fine scale structure, as we were hoping, since we're really close to those events compared to 1AU. These are not, they're only, on average, I would say 20, 30 solar radii away from us. At least in these cases that we did a quick localization, right? So there are some issues, of course, now for treating the data. One thing is, okay, now we see a lot of structure. How can we learn a little bit more about it than we can from 1AU? So this is something we working with Alexis for a while. This actually started back in SECCHI to try to take the Jim Chen model, which is a very practical, if not fully self-consistent magnetic flux rope model, but it's very easy to incorporate kinematic measurements to it to understand to come up with something about the magnetic properties of the transient, and try to make it a little bit more realistic, because the original one was circular. It had the same sort of, it was basically a cylinder. So what Alexis has done, along with Valbona Kankel and the other people at IRAP, is to come up with a better profile, which is self-consistent with the magnetic field, assuming a Graz-Franov type field, for the shape of that flux rope that we see in the images. And the details are in the paper. I just have the equations here for your reference when you look at the talk later. And then solve the force balance equation. So the new thing is this inductance, which still is not, I would say, satisfactory, 100% satisfactory, because it still assumes a cylindrical, a circular shape for that slinky. The next step is, of course, to make this elliptical so we can study distortions. But it works pretty well for now. So the force balance equation takes into account the gravity for when this, takes into the gravity because we start the eruption low in the corona. So we need to incorporate that to capture the early kinematics of the event, and of course the drag force that can operate against or for the CME in the later stages. And you can see how that is applied here. So this is the flux rope CME that I showed in the first slide from WISPR. We looked at that. We focused on that because first of all, it has a very pretty cavity in the center. And so what you can do with this model is basically you can modify that slinky flux rope until you capture the outer envelope, let's say, of the transient. But the advantage is now that you can actually, solving the Grant-Safranov equation, you can come up with a self-consistent, I believe, idea of how the currents or the field lines look like. And so here in this middle picture, for example, you can see that according to this modeling, we have a poloidal, poloidal field, but there's still and the toroidal field colored differently. So it's a slightly sheared or twisted flux rope. Now that allows us to come up with an estimate of the magnetic content, which is about 250 nanoteslas at that distance from the sun, but also allow us to fit the kinematics of the CME. So here on the left-hand side, in the middle panel, in the red red points are the measurements using all available data, including EUV, low down, and then LASCO or SECCHI and WISPR. So this, of course, it's a solar minimum event. It's very slow. You can get good measurements of the slight slow rise. And so you can get these time measurements, put them into your force balance equation, and try to fit all that, of course, making some assumptions about the background solar wind. One of the free parameters is the poloidal injection. How flux is added to this flux rope through the connection that helps it accelerate. And what we found in this paper, which is quite interesting, is that in order to fit this sort of break in the acceleration profile, we had to assume two injections. One early on when the flux rope was really close to the surface, which is what we would usually associate with the flare, the flaring or the impulsive flare, passive phase flare of the flare, which sort of in this case is interpreted as getting the flux probe to move out. But then we had to include an additional reconnection event to get it to accelerate. And this event, if all this is true, happened when the flux probe was at 3 or 4 solar radii. Well, I mean, so that the CME was quite far out of the surface, which you would think that you wouldn't be seeing anything in the flare. Now this is a very, again, I say it's a minimum event. There's not much. There's not a flare on the surface, right? Whatever it is, it's a very faint. But it is interesting to know that, yeah, if we had only a single profile, we could not fit the kinematics from all these different instruments and viewpoints. So this is kind of encouraging that we will be able to get into quite a sophisticated analysis of energy injection into the CMEs with this, by analyzing more events. So this was like a proof of principle fitting. Now, to get the kinematics, though, things are complicated. That's why I said before, the observer, the WISPR is not standing still. We're moving relative to the transient. And since these are really slow CMEs, 300, 400 kilometers per second, we're actually moving at considerable speed relative to them. So Paulette Lever and I and Chong Chu, we started a long time ago looking into how we're actually going to fit the kinematics. And there's a paper that's just been submitted to Solar Physics, where I'm not going to go into all these details, but basically, in order to fit the kinematics, we have to project everything on the orbit plane, and then use and measure the distance of a CME point here relative to the orbital plane. Here is beta and gamma are the two angular parameters, and then do this step by step. Basically, consider the orbit of the probe to calculate these angles. Work only at in angle space, not make it solar radii or anything like that, and do a two-step fitting to get everything, to get all the parameters. Now we have to assume that the CMEs are propagating at constant speed, and they're not and radially. These are two constraints. So these are an example of again, looking at the CME from November 1st, which is the one I showed you before. With Paulette chose two different points that were well defined. This is sort of the interface between the darkness of the cavity and the sort of the pile up at the back, and then what we usually call the V disconnection point in the CME, and try to measure it far as we can. And this is sort of a snapshot from the paper. So we're taking different tracks, trying to get some sort of an idea of the error pointing measurements. And then these are the two angles, the gamma and beta, one on the plane and the other one out of the plane. And there are a lot of there's a lot of trigonometry there. Basically, trying to fit this ratio of tangent beta over sine gamma to get something that matches the high time points. Now the thing works. You can see here in the bottom. So first we try to fit the data, then we take this beta and gamma and we put it into the equations that give us the distance and angle, the heliographic angle of the CME, the propagation angle of the CME. And it seems to work very well. You can see here fit error of 0.02. And that's because, of course, we have no errors in the actual points themselves, right? When we say that this point, for example, is at 25 degrees, we don't give it any error. Because, again, this is a projection of a three-dimensional structure. So this point potentially can be in slightly different angles depending on what you assume for that line of sight depth distribution of the density. So we're not there yet. This is just a beginning, similar to what we were for SECCHI in 2008. We had to make the sort of the simplest, most obvious assumptions and work the algorithms. But the way to try to validate the measurements is that once we have the high time points in an angular in the orbit plane, we can then project them into, say, the high or the LASCO viewpoint. And so here's our attempt to validate this measurement. So these are the measurements that we took on WISPR projected onto the closest image from SECCHI high. So you see that they're quite close, but for example, this red point corresponds here in the bottom. Look at the bottom panel, corresponds to the back of the cavity. But you can see here that it's a little bit off, a few solar radii off. So that's the next step now. Is this really an error, or we're looking at different parts of the CME from 1 AU and 30 solar radii? I think it's the latter, that Thomson scattering effects really play a role here, and I think they're key to allow us to do a very detailed 3D reconstruction of these transients, I think. But that's the first step. We haven't moved to the next step yet. But it works. So actually the overall direction of the transient matches what you would get from LASCO in core 2 to within a few degrees, and with a source region on the surface. Now there are other interesting CMEs. This is like hot off the press. This is from the 4th perihelion in January, where we got the data in mid-May. And this is my first sort of look at the data before preparing for the preview for the E5. So this actually, we caught a CME when we were flipped. We were flipped 180 degrees so that the probe could transmit to Earth. And it so happened that there was a very big, pretty flux rope CME. And here's a snapshot of what you see here in faintly in the data of flux rope again, with a very dark cavity in the center. Again, a pile up at the outer ends of the cavity. But this also has a lot more structure. And so we only have a few images, but I think they're quite sufficient to analyze this event. Now, the interesting part of this event is that we crossed it. Actually, some of I'll try to stop it at the right time here. Maybe I can stop it. And I'll try to see if you can see a very faint structure in here. That looks more like a dark structure. Here. So this part of the CME, it seems that we actually crossed it because the in-situ instruments detected a flux rope, and we saw particles. Very weak particles, of course, because it's a slow event, but still, I was surprised to see that there was a signal. I'll come back to those particles because this is one of the interesting findings from probe overall for the future. So that's for CMEs. Now dust-free zone. The dust-free zone is something that we were aiming to do with WISPR, because now we can go inside the dust, basically, that surrounds the sun, and see if indeed there is a dust-free zone as predicted for 100 years now, due to sublimation of the dust due to radiation from the sun. So this is a raw sequence of WISPR images. You can see the challenge that we have, that the F corona changes, although you can see the CME passing through. And without getting into too much details, I can show you what we're finding. A lot of these lines are what we've been measuring from SECCHI, and as we were approaching close to the sun, And the prediction was that, of course, this, if there's no dust depletion, all this will go is a straight line all the way to the sun. And early on, from the first sort of observations, we start seeing that a lot of our lines of sight deviate from the prediction. So that's an indication that there is dust depletion. So what we were waiting for basically is more data from this fifth perihelion to see if the trend holds, so that you can then make the big claim that we're actually detecting the drop in the dust. So if you're a dust aficionado, that's it's pretty exciting news. There is more dust stuff here. There are more details. I don't want to go into that. This is, we try to do different models because the change is very small. We're talking 10 to the minus, if 10 times 10 to the minus 9 solar brightnesses. And so we try to do different models, try to ensure that we're really seeing a depletion. Is not like for example, our detector has lower efficiency close to the sun because it saturates and all those things that you have to worry if you deal with instruments. So we think we are in the dust sublimation zone, and then at some point, maybe even from the next orbit or in a couple orbits, we might actually start seeing directly in the images that the dust drops completely, if there is indeed a dust-free zone close to the sun. So this is all Guillermo's work, and we prepared a paper on that. Now, the other thing, of course, we found was that we actually see the dust ring that Venus is gathering as it goes around the sun. That has been postulated before. There were some early indications from SECCHI, but now we actually do it. We see it direct, straight in these images. And in the beginning, Guillermo and I thought that we had a problem with the data because this was always there, and we were thinking that the model was not working right. But Guillermo figured out that this is actually the dust. Here is a zoom in of it. It's a very bright signal actually in the data. Weird. I guess I didn't know that we're going to be doing dust work, but apparently we are. And another one that has nothing to do with the sun, but it is quite takes quite a lot of interest, are comets and asteroids. So here, this is going to be a tricky one. I don't know if you can see this very faint. You're going to see a very faint streak that moves and rotates in the image right here. This turns out to be the dust trail of Phaeton, which is an asteroid that behaves like a comet. These are actually the measurements, and this is the direct imaging of Phaeton. There's a paper that Carl Battams wrote, where we can actually do brightness measurements and then estimate the amount of mass that is on that orbit, which has not been possible to do from Earth. And it's quite timely because the Japanese are launching a mission to actually go and study this asteroid. So this is quite important for them because, of course, one thing is you don't want to get hit by all the dust as you approach. This is also the origin of the Geminid stream, which is might be a concern for probe because we're actually crossing it on the way out of its perihelion. And so this is something we're monitoring closely. That's why sometimes you notice in the WISPR images, you might notice a lot of streaks after the perihelion than before. There is a marked statistical change in the amount of hits we get because of the Geminids. Now, because of that, we have been actually doing a lot of spatial comet observations with WISPR, and you will see maybe in the future, and if you look at the data, you might see that the spacecraft flips a lot, particularly in this May, because we're going after Atlas and Enki and NEAR, actually. So we're doing a lot of that. Finally, for the WISPR small scale, this is what still in the beginning. This one we do not have yet good WISPR small scale stuff. So this is a synergy between Core 2 on SECCHI and the in-situ instruments on WISPR. This is a period in in the second perihelion in April '07, where core 2 and core 1 were looking at the plane of the sky, basically, of the outflow from the sun that was crossed by a probe. So this is the streamer that the probe crossed, and of course we see quite a lot of blobby variability all the way to high, where that's the distance pretty much of where probe went through. And so when we actually do the J maps from core 2 and high, and compare them with the measurements, the in-situ measurements for probe, we see that there's a very, of course, good correlation. Every time you see these big gaps here, big the dotted lines, this is when one of those bright density features we're supposed to encounter probe. This is the probe path through here. And so what we see basically is that, right, whenever the probe passes through one of those enhanced outflows, you see a lot of what they call switchbacks. Basically, the magnetic, well, the magnetic field is not here, but you see a lot of switchbacks, and they last, this variability lasts for hours, as I have here. But it's very clumpy, so on the streamer belt. Now, when we are in the open field, it's less clumpy, but of course, you see that there's a lot more of that small scale velocity and density. I mean, velocity variation, but not so much in density. Despite what we thought we intuitively what we would expect, but it's nice to see now that we can do a one-to-one correlation of those studies and eventually be able to track them closer to the sun and see their properties. So this is basically that leads to the couple of other findings. I think it's a bit late. One is what you might have heard about this variability in the magnetic field that Fields has detected, where you see here the magnetic field as we go through the current sheet, and you see very sharp changes in the radial magnetic field direction, plus to minus. And so they are interpreted basically as kinks in the magnetic field that propagate outwards, kind of like when you have a lasso, you see the kink propagating along the field lines. And one of the big now efforts around the community is to figure out where they're coming from using ground-based and EUV, X-ray, and all these other observations. Try to track. Of course, it's very hard to track magnetic field changes back, since we only see density in most of our instruments. We see density changes, but that's a big focus of the community right now. The other one that is quite surprising, maybe for the in-situ people, but not so much for the coronagraph people, is that they see a lot of extensive co-rotation. So according to these simple-minded models, you expect that the corona will become supercritical around 10 to 20 solar radii. And so therefore, from then on, the magnetic field should start, you lose co-rotation. Now, what SWEEP is finding is this is the expected transverse velocity versus radial distance if you rigidly rotate. This is what the model predicted. You know, above 10 solar radii or so, you basically lose. you don't communicate with the sun anymore. And these are the measurements from different perihelia from SWEEP. So the transverse velocities are quite high, about 10, as they say, about 10 times, I think, higher than model predictions. So it seems that the correlation goes from farther out, but this is something I mean, royal we, not me, but a lot of the coronagraph people notice in the beginning of LASCO that although LASCO C3 goes out to 30 solar radii in projection, we never saw the particle spiral or evidence for particle spiral, even for very bright streamers that we could trace beyond, I mean, at the edge of the field of view. So there was this indication that the model is not quite correct, and so this is proof that there's something fun is going on there. Now, for the diegetic particles that are a little bit more closer to us, what even though it's very minimum. ISIS keeps finding small particle events throughout the orbit, and this is a representation that you see in many of their talks, where they split the two ranges on either side of this orbit line, and then they present the intensity of the particles. So you can see here, for example, that in the first perihelion we had a low in the low energies an event. Then in the high energies, some of them are associated with CIRs, but not all of them. And one of the interesting ones is an event that actually had heavies on April 2nd. This is the data from ISIS here in the center. Ed Roloff is leading this effort, and I'm helping him with that. That we saw a very sharp increase in, again, we're talking about small energies, right? Talking about hundreds of kVs. Very sharp increase, and then a very sharp decrease of the particles that lasted for 18 hours or so. This was associated with a lot of radio bursts. The decrease was associated with crossing, with a boundary crossing. Basically, we went from being on the slow solar wind, we crossed into a corona hole, and that's where the particles cut off, like within 10,000 kilometers or something. That's crazy. Now, where does particles come from? The good thing is that probe was right in front of stereo A at that time, and this is a movie I made of that that period. So we have so the probe is basically, you can think of it somewhere here in projection, and you have this active region on the east limb that keeps giving out what surges all the time. That every surge almost is associated with a type 3 or a very weak type 3, almost all of them, and that lasts for days. Now, when I looked at the ones that were more closely associated with these particles, and this is easy because we are 40 solar radii away. The particles are coming radially, so it's very easy to go back and find where at what time they were injected. And this is a running difference I made of one surge that had actually a wave, or wave, followed by another surge within 5 minutes, and the two waves interacted, creating a much stronger front. And that was my interpretation for this, that we had the shock acceleration of those particles. That's why we got these high Z's. The question is why we have them for 18 hours. And there is very little ambiguity when you're so close to the sun. Basically, you know the particles are coming radially for 18 hours from just the sun. There's no, there's very little leeway you have to play with transport effects here. So it's basically you are inside a hose of energetic particles and you're following it around because we're co-rotating on top of that. So Ed is working on the theory on this one. He's very excited. I don't know when he's going to write the paper, but this is cool. Now, what are we doing in the future? Things we should know is that there was Orbit 5 just came down, and we're supposed to release the data publicly in 3 months after that, so in October. Orbit 4 will be released on August 11. We have a Venus gravity assist on July 11, and we're going to be doing special observations for including, I'll try to take images of the Venus clouds, because why not? And then with Akatsuki and ground-based telescopes. So this is, and there will be a special issue GRL, I think, for a lot of the in-situ studies of the Venus magnetosphere, actually. So that's another thing that probe does. Now, okay, we have last forever. Here is, so what I want to leave you with, you can find all the data through either the Parker Solar Probe main gateway that sends you to the instruments. For WISPR, you can go to the instrument directly. And there are different levels for WISPR, level 1, level 2, level 3. Level 3 are the images that I have basically processed to remove the F corona. So in principle, those images would be as clean as we can get them at the moment. Level 2 is the images that are calibrated, but of course they have the F corona, so then you can use those to do your own analysis and try new algorithms and all that stuff. And so the data is publicly available. Everybody can use it. If you have questions on WISPR, of course you can ask me. We have a WISPR science team email list that includes quiz, and people that were interested and gave me their emails so they can participate in discussions. So that's all I have. Thank you.
Thank you, Angelos, very much for the nice talk, for the interesting new results. Wow, exciting times.
The last stuff, yeah.
Other questions?
I would have a question.
Yes.
You showed these results on the transition between the corona and the solar wind.
Mm-hmm. Yep.
And there, it also mentions that this may provide some hint that the young sun was rotating faster than we are thinking.
It might. Mm-hmm.
Can you tell the connection here? I'm not sure if I understood it.
Well, I don't understand much either, but I think it has to do with the angular momentum loss that you can work backwards. You know where that radius is now, where it could have been when the sun started, and assume some sort of angular momentum loss, which will get it to 10 solar radii. But now, I mean, to 20 solar radii. But now, if it's still co-rotating rigidly, it means that originally the sun had higher angular momentum. So I think that's the top level explanation, that it was rotating faster than the models seems to suggest.
Okay, thank you.
Yeah.
More questions?
I have another one.
Okay.
Nobody else does. Right. You showed this kinematical profile, which looked actually quite straight to me, but then you said you need, with the Gen model, this double flux injection to model this evolution. But why? I mean, from the profile, it doesn't look obvious to me that there's something happening again, but.
No, it doesn't. It doesn't. For the high time measurements themselves, it doesn't. But if you were to solve this equation with only one profile, and I didn't put this figure, the figure is in the other paper, then this was completely off. I think it's.
So you mean to fix the flux rope, the magnetic pressure inside, or? Yeah,
this is to make it. This is, of course, under the assumption that the propagation is like what Jim said. You know, it has to do with the expenditure of magnetic energy to propel the structure out. So under that assumption, then you can solve the force balance equation and then come up with these interpretations. Yes.
But there was no flare related, or
no. This is well. Also, that was on the far side from Earth. But it took about a day to actually move through the EUV and core one field of view. That was very, very slow, and then it went very quickly. So it took us a while in the beginning to actually find the source region for this, and a lot of it was behind the west limb.
Would this second injection also hint towards solar wind acceleration itself, which then is also applied to the flux rope structure? Yeah. So there is, I think it is accelerating by the solar wind in the end. Yeah, that the drag force is actually positive, right? Right. It helps it to accelerate. Yeah. With such a low speed, there is not much driving itself from the Lorentz force, so it should be a positive drag force. Then, yeah. Yeah. Now the interesting thing is that the same event is this the 11th? Yeah. So one of those events actually had particles inside it. It was crossed by ISIS. I think it's November 12 CME, which looked very similar. But it was on the other side of the sun, on this limb, and that actually had particles in it.
even though the speed was only 300 kilometers per second. Yeah, that's kind of, they've been finding particles left and right.
Yeah.
These things.
I mean, anyway, if I may just, if some other questions you can ask, but I guess just go ahead. You show actually on this slide that there is a this cavity that you see. It kind of nicely matches with the angle of the streamers. I mean, with this, how far the streamer is apart. So does that hint towards, I mean, really some streamer, some blob within the streamer belt, something like that? So is it, because it really goes,
yeah,
the structure really nicely.
Yeah, the width of the structure is.
It's with the angle of the streamers.
Yeah, it could be, but this of course is a big CME. They did a reconstruction. I think Brian Wood did a reconstruction of this. It's quite a long CME. Not Brian Wood, Phil Hess. So it's a pretty big event, and we only seen, of course, the part that is projected on the sky plane.
Right.
And it might be just a chance because we see in the other cases it's not exactly so perfectly aligned with the streamer. But yeah, in the beginning, I'm still, we have to make a lot of assumptions about the background. So you can see these black lines here. To me, they look more like background subtraction effects, and so not clear voids.
The streamer belt might also, how the structure looks like, might also come.
Yeah. So that's what we're trying to understand better. The three-dimensional structure of that belt to get a better handle on that background subtraction. How much K corona we're taking out.
Right.
The interesting things in these events is the pile up at the edge of the black of the cavity, because that signifies that there is magnetic force. The cavity tries to expand and it's piling up plasma on the outside. I mean, still inside the big flux rock, but yeah, that's an interesting thing.
Some more questions?
Hello, Angelos. I'm interested. I'm interested about blobs that you mentioned. Do you see any quasi-periodicity in these blobs, occurrence of these blobs, or is just sporadic?
At the moment, well, the periodicity that we have in these other blobs, the ones we see from core 2, these ones, these ones are mostly hours. So they are 6 to 20 hours. So these are macro scale quasi-periodicities. We try to go to the finer scales, and we don't have enough signal to noise ratio. Everything is too faint from the sun to actually be sure that we're detecting any periodicity. We try to go down to 5 minutes, and it's noise at the moment. It does look like there is structure at that point, but it's just barely above our detection threshold. Yeah, so I try to do different observing programs now to see if we can catch something, but the sun is not cooperating. It's very the sun is very weak. Yeah.
As far as I know, there is some hour periodicity or something like this.
Yeah, the hour periodicity is there.
Okay.
And for sure, try to see if it gets if it gets lower. That's what we're trying to get. Yeah.
Okay. Thank you.
Thanks.
Hello. So this is Tatiana speaking. Thank you very much for a very nice and interesting talk and showing us a lot of interesting plots. I have a question. You have so great background picture. It looks like from ancient times.
Yeah,
what is it? Who did it?
Well, I found it on the web. I don't remember where it is, but I think it was in the NASA website that has the classic, sun-earth connection. That's why a guy looks like Galileo's paintings. That's
Yes. Very great.
Yeah.
More questions?
Yeah. And for the data too, you know, the data analysis, there are other questions.
Yeah, just asking. I mean, one more question on this event when you said you measured particles co-rotating with the event. So could that be an opening of magnetic field? And do you have an idea about the energy of the particles that you measure compared to the magnetic field of a presumed open flux is located at that point? Because you said you can trace back to the solar surface, right?
Yeah. So the particles, you know, they're energetic particles, but of course they're very low fluxes. This is not, they're not detected, for example, by STEREO-A, although it's radially aligned with a probe. The type 3s, they are, so we have KV electrons, but the actual particles are, you know, less than an MeV, and they're so if you sum up the fluence, I don't know the number off the top of my head. You know, this is EDS stuff. It is not that much. The problem we have is that this requires a sustained acceleration agent to get these particles for 18 hours continuously, because there's no modulation. There is no that you say coming in and out, or there. For example, that it doesn't agree with all these continuous jets. I don't see it like a spike every time you see a jet or a surge in the surface. They only start when we have those two big jets.
I mean, would the energy be comparable to a quiet sun region, but where you have an open field, where you actually just the energy that is naturally coming from below, but it's not.
No, at least a little bit more, because we get some heavies, but I don't know the energetics of this. We also, you know, in principle, you know, if you were to do this analysis as we do from 1AU, the foot point of the probe will be here.
Mm-hmm. Okay.
And the particles are coming from here.
Okay.
And there is a corner hole in between.
Yeah.
So obviously the connectivity, the standard connectivity does not work.
Mm-hmm.
Obviously, we know from in-situ measurements, we are connected on this side of the corner hole because of the in-situ, you know, the densities, and it's all quiet sun. And so that basically we're maybe connected at the edge of open and closed field. And I think that's what could have created the original particles, is the compression of from the two successive surges, bringing the wave, and, you know, and pushing the magnetic field at that boundary, and creating some compression that can allow particles to accelerate particles through compression, not through Fermi acceleration. But then you need to sustain this for 18 hours. So unless there is a reservoir somewhere, it is interesting, yeah, because we're getting these particles around quite often, it seems. I mean, not this high, at high ions, but in protons and electrons, you do get a lot more slow level variability than one was expecting. And it seems to me that, to me, this event alone suggests that the sun can accelerate particles very easily, and that may be the seed particle population that we've been discussing about. You know, if these surges can do so much damage, I mean, then anything can send particles up. It's like, yeah, we have never noticed the surges until Ed came running in the office and says, you know, what is happening?
Well, more space weather tools are needed for that.
Yeah, so be ready. There will be a lot of onslaught of this type of background events, and, you know, particles, and what is a CME or a blob creating it, and all that stuff. There will be a lot of that.
Okay, thank you.
Mm.
More questions on the talk? Yeah, then a final question about data analysis. So there are solar soft packages, I assume.
Yeah, WISPR is, yes.
WISPR is in, right? So
yeah, you should update SolarSoft with the WISPR package. That's just the probe. You have to have both of them on. Also, SunSpice. Make sure that you update SunSpice package often, because we need to use that to care if you want to do any sort of localization in space, now you have to use the attitude kernels of the spacecraft. That's something we usually care about for SOHO, but here you do. And so these are released, predictive kernels are released, I guess, ahead of time, you know, months in advance. But then after the fact, the spacecraft will release the actual attitude of the spacecraft. And you need this to know where WISPR was pointing, where ISIS was pointing. It is important because there are a lot of pointing changes during a typical encounter. Yeah.
Are there any tutorials online or?
For the SunSpice, there's only really a Word document.
WISPR data analysis.
Well, the WISPR is basically a WISPR prep. There's a WISPR prep routine, and to read in the files, and there's a WISPR read feeds that actually populates the header with all the keywords, and then on the header itself, we have pretty much everything that you might want to use instead of, so you don't have to run SunSpice. On the header, you have all sorts of the heliospheric, heliocartesian, ecliptic, all sorts of different projections information, including the distortion of the images. Now, what I'm working on releasing is this package that does the projections in different orbits, because this is from JPL, you know, Paulette's thing, and they're giving me a hard time about it. But it will come, sure, soon. You know.
So you would advise to work on level 3 data because the corona is.
Yeah, the level 3 data for sure, because that will be the cleanest ones. But if you're going to do only running differences, for example, or base differences, level 2 is okay, and you don't have to worry. Then you can remove the stars, for example, or planets yourself if you want more control on it. But yeah.
I mean, so
level
far
1, no.
Data, but
yeah,
but we didn't really have the, how to say, the courage to go over.
Well, me neither. I don't do much in I do L2, but they'll be released, and of course, from time to time, if we find a better way to process the images, we're gonna release the L3s.
Right.
Okay, so for example, now I would say to wait until August 11, for example, now, because we're gonna reprocess all the data and release it along with the 4th perihelion one.
Okay.
Yeah, I think Phil has a better photometric calibration now.
Yeah.
And the artifacts, these are detectors that are APS detectors, so they're not CCD, so you should be careful. There are some non-linearities there at certain places, and yeah. I mean, if you say if you're suspicious of something, just email me.
Yeah, sure, absolutely.
So they know that if this, you know, it's real or not real, you know.
Yeah, absolutely. Yeah. Thanks a lot.
Good.
Yeah, are there more questions from the audience? Nope. I guess I take the silence as a no. Okay. Then I would like to thank you, Angelos, again for this following our invitation. We had more than 30 people attending, so that's really nice.
Nice, I'm happy. Yeah.
Next time we will beat Whippy, and then we. No.
Thank you. It was great to see you all. You know.
Yeah, it was nice seeing you again, talking to you again. I wish you a nice day.
You too. Enjoy.
Yeah, you might receive from us with questions about data analysis in the near future.
Yeah, absolutely.
Okay, great.
Thank you.
And thanks everybody for attending, and goodbye to everybody. Have a nice day. Okay.
Okay.
Bye-bye.
Thank you. Thanks all. Bye-bye.
Bye. Bye.
Thank you.
Thanks. Bye.